very much, everybody. So yes, I'm going to give you a whistle-stop tour of various ways of adding high performance into your Python programs, and see if I can convince you to come along tomorrow to spend the afternoon with me learning it in a very practical session. So the goal will be to get you to write your CPU-bound tasks in a way that executes possibly using C code as transparently to you as possible, using just plain Python code more efficiently, using multi-cores and potentially multi-machines, and going all the way down to using a CUDA graphics card for very highly parallelized computing. And this is actually the tutorial for tomorrow. I'm just going to run through it really quickly and show you the demos. There's a whole bunch of stuff to download. There's some source code, 5 simple files, which are available online. But I've also got 4 USB sticks, and I'll be serving all the data up via this machine. It's serving now, and it'll be serving tomorrow. There's also 200 megs worth of binaries that you have to choose between to get the right compilers and rest of it on your machine. So if you're interested in taking part, you want that all set up beforehand, not when the tutorial starts tomorrow. So I'll be around after this talk, and I'll be around before the tutorial tomorrow. I need you to come along and get things installed on your machine, and possibly find the things that I didn't manage to download over 3G this morning. I tried all combinations of all the major OS different versions, but I've bound to miss something. So we need to get that sorted before we have the tutorial tomorrow. So a quick bit about me. I'm an artificial intelligence researcher. I came out of university about 12 years ago, straight into industry, 6 years as senior programmer in an AI startup between Paris and the UK, and then 6 years or so running my own consultancy, working mostly in Brighton in the UK and London. And that's a mix of hands-on AI and high-performance computing. So a lot of that comes down to, we've got a hard problem, how might we solve it? Now we've solved it, it's incredibly slow. How can we quickly make it faster so that it can solve our problem properly? I've got a mix of C and Java and Python. And if you were at EuroPython last year in Birmingham, on one day in the lightning talks I had a little robot head that tracked me around stage, and the other day I showed the PyCUDA demonstrations. I showed really fast Mandelbrot set calculations, which is part of the basis for the tutorial now. I lecture one of the founders of ShowMeDo, which some of you may have found video tutorials, and I teach Python. These are all the things that we're going to be using in the course. So one of the first things we have to do when we have slow code is profile it to figure out where the bottlenecks are. The standard tool for that is the cProfile module that's built in, and RunSnake, which visualizes it. RunSnake's awesome until you want to find out which line is really slow, and then it's useless. And that's when we switch to the line profiler. And we'll be using line profiler quite heavily. That's a tiny module to install. And we'll be working through how to speed up our code, and with reference to the lines that are slow. So we can basically go through the process that I use when I've got a chunk of code and my boss says, hey, there's a bit of code, it now needs to run about 3 orders of magnitude faster. I'd like it in a week, please. And then I have to just get to work. So we're going to go through that process. We're going to use NumPy, which is the numerical Python library. It's supported by Nthor, which are outside. They've got loads of demos if you're curious. Great for vectorized operations. So you've got a big array and you want to do the same thing to 2 arrays, 3 arrays, 10 arrays. We'll do that very quickly for you, which is great for the Mandelbrot set example. Cython and Shedskin, 2 different ways of compiling your Python code down to machine code using a compiler of your choice. Cross-platform, I'm running it here on the Mac, I've got it running at work on Windows and at home on Linux box. The multi-processing module, so I can spawn sub-Python executables across all of the cores in this machine. So 2 or 4 will be quite common for a desktop or a laptop. The parallel Python module, which lets me use multi-core and multi-machine multi-core. That'll be at the end of the talk tomorrow. Given all the Wi-Fi issues, I'm not sure that's going to work across all of the machines. What would be awesome is if I can get a really big Mandelbrot set with a high number of iterations being calculated across a number of our machines all at the end of the talk. PyPy, I've barely used PyPy, but I discovered it's awesome on this problem because it runs 3 times faster. Did any of you go to the PyPy hands-on this morning? I missed it. Did anyone go? Yeah? Okay. Maybe you can have a look at my code after this and tell me if there's any obvious tricks that you learned this morning that we can stick in there. So I'd love to share some knowledge if there's knowledge to be shared about PyPy. It's a really nice, easy win. And finally, PyCUDA. Does anyone here have a burning desire to learn how PyCUDA works and actually practice it? So 2 people and a couple more. Right. How many of you have the NVIDIA CUDA development kit installed on your machine already? Oh, okay. Okay, well, we might do a tiny bit of that at the end then. I'm happy to talk about it afterwards. It's a bit tricky. You have to have the CUDA dev kit running on a machine with a CUDA graphics card, and then PyCUDA itself has a bit of a tricky setup process. It either works fine, or you spend half a day on it. And I've done it enough times to help refine the process. I don't know if you've got an NVIDIA graphic card in there. I don't know the hardware. I'm happy to have a look at the end and have a chat about it. But yeah, certainly we'll go through the 3 types of demos and see what we can get out of the machines. So we're not going to be looking at algorithmic choices. We're going to have a set problem, the Mandelbrot, with a set of arguments that go into it and an output that we want. We're going to preserve the arguments going in and preserve the output coming out. We don't want any variation on that, so we're not going to look for any algorithmic shortcuts that might approximate problems. I'm not looking at that class of problem solving today. We're not looking at cluster solutions. We'll look at multi-machine just as a quick look at the end. But we're not looking at clusters. It's really about getting the best performance out of one machine, which is the typical environment I work with clients where you've got one person developing on a machine and they may have access to an office work of machines. We're not looking at cloud deployments. We're not looking at GNUMPy, Theano and Copperhead. They are 3 really nice, interesting projects that pretty much take NumPy-like code, the numerical Python library, and convert it to run on the GPU or on its CPU and GPU. It looks really awesome. I haven't had time or practically to use it yet, so I'm just not covering that. Bottleneck is a lovely library where the Cython C compiler is wrapping up bits of the NumPy numerical Python library. So bits of NumPy is specialized and compiled down to C, and it runs even faster than NumPy would ordinarily run. But it's only got a bunch of functions that are useful. They're not useful in this case, so we're skipping it, but you might want to have a look at it. It's really easy to use. We're not covering MapReduce or that class of solution, and we're not looking at OpenCL, simply because a year ago when I started with CUDA, OpenCL was pretty rubbish. Now it's kind of feature parity, and certainly PyCUDA and PyOpenCL are supported by the same guy. They're at feature parity, but I just don't know OpenCL yet, so we're not touching that. Okay, we'll skip that for tomorrow. So let's have a look, what kind of speeds can we expect? So this column here is Python. So this is a collection of numerically intensive benchmarks comparing a number of languages together. It's the Codemania language benchmarks game. Has a bit of controversy. It's a pretty reasonable way of letting you, the community, upload a solution to the problem that uses the idiomatic form of the language. So you're not trying to super optimize your language implementation, you're just getting a good language implementation so we can compare how various languages run the code. Python comes out pretty damn slow, but it beats PHP and Ruby. We'll look at JavaScript V8 somewhere down there. The average solution time is basically 1 order of magnitude above C, which is the best. Python is quite far away from that. But with a bunch of the techniques that I can show you, we can take this average bar and bring it all the way down to roughly within 1 order of magnitude of C or better. And there's, just to give you some real numbers, this language benchmark came out quite recently, a couple of weeks ago, I think. So we've got a number of problems like Sudoku, matrix multiplication, and a bunch of others, and then implementations across a number of languages. So C using the Intel compiler, GNU compiler, and a bunch of others, JavaScript V8. We see on the Sudoku 1 second for the Intel compiler and GCC, 4 seconds for JavaScript V8, and CPython 100 seconds. It's useless. It's 2 orders of magnitude slower. That's really, really bad. But if we go to PyPy, with no work, it's only 1 order of magnitude slower. And if we look at Shedskin, which is the automatic Python to C converter, it runs in 4 seconds. So it's in the same order of magnitude as the C implementations, but you've written just a handful of lines of Python rather than having to write a lot of C. So we're going to be looking at Shedskin and CPython. So hopefully getting into the realm of C-like speeds, having written just Python, and learning a bunch of relatively straightforward techniques that we'll find that way. Should inspire you if you want to solve this kind of problem. So here's a practical result. One of my employers, I'm a consultant. This is ex-Philips Analytical Research, analytical 800-man European company, make expensive physics machines, working on a solver which My boss is a very smart man at that company. He's revolutionised the industry once 20 years ago. He wants to revolutionise it again before he retires in the next 4 years. He's redefining the fundamental theory of Bragg's law, which will redefine a tiny, tiny niche, but a section of the physics industry. To do that, he has a large computation that requires solving before it can get into nature. He gave me the numbers, I ran the numbers, and I said, boss, it's going to be fine. We only need 1,000 machines running for a year at Amazon EC2 on the largest cluster instances. It will cost about £1 million. He said, no, we can't do that, we haven't got the budget. So I've been optimising the code. Each time I give him an order of magnitude speed up, he then goes and puts another for loop in some way to make the simulation better, and I have to start again. So where we started a couple of months ago, 234 seconds, using a mixture of Python and the EuroPython library. Then I added some more NumPy over another couple of weeks, and I got it about 30% faster. A little breakthrough by doing some analysis on the code. I realised that putting in an if statement meant that I could cut out about 25% of the calculation. That's kind of awesome. Then I stepped back, went back to the original code, so the right from the left, 234, and just used some Cypher in there. And so I got the 234 seconds down to 90. Then I combined the previous results, the 126 seconds, with the Cypher and got down to 81 seconds. And then I made it run across 4 cores and got it down to 20. And that was the result Friday before I flew out there. So that's quite a nice solution. That's going to have to scale up further for bigger approaches to this problem. But that's all achievable within a couple of weeks. And so we're going to be looking at the Mandelbrot set. I'll show you in a second. Just to give you a range of results. 35 seconds, the leftmost graph. That's a pure Python implementation. Switching in PyPy on exactly the same code, it drops down to 10 seconds. It's kind of awesome. Switching to numerical Python with the vector library, it's worse at 36 seconds, and we need to have a look at why. It turns out a vectorized solution is not the most efficient way to solve the Mandelbrot problem, and we can have a look at that. But then adding in the numerical expression library, which is 2 words you wrap around your NumPy statements, all of a sudden it goes over 3 times faster. That's for free. You import one module and then 2 words around a couple of statements, 3 times speeder. And the Nthorpe guys outside have got the math kernel library version of NumExpra running inside the Nthorpe distribution of SciPy. Which makes, if it's got it available, to use even more cores and more vectorized expressions on the machine and running faster. There's a Cypher solution down to 0.3 seconds in Shedskin. And so there we're looking at 2 orders of magnitude speed up. For very little work, we'll be going through that in half an hour, and you'll know exactly how to do it when you're running problems after that. PyCluda, running with the high-level expression syntax, so a NumPy-like syntax. You can learn it in half an hour, but it's not super efficient, and there are many overheads which we can discuss tomorrow, so 3.5 seconds. But when we wrap up the PyCluda with a bit of C to express the underlying Mandelbrot problem, which is the kind of code we could pull out of something like the Shedskin result, we drop down to 0.07 seconds. It's running on a high-spec machine with a £400 gaming graphic card. Nothing too special, just a GTX 480, cost €400 a year and a half ago. But that's a 500 times speed up between the original Python code and the Python C version. And in the parallel Python version there, we're just taking a straight interpreted Python and running it across multi-cores. We get a 4 times speed up, which is kind of nice. So I'll just skip through and show you. So this is the first thing that we're going to be looking at tomorrow. This is the slow implementation. It's a bit of C code that loops around an array of pixels, just doing many calculations, 1,000 loops, it does roughly 1,000 loops, calculating the Mandelbrot set equation. And it takes quite a long time, and you look at it first, okay, there's not much I can do to this, but there are some things we can do to it before we even have to do any high-level work with compilers. Just take about 55 seconds to come through, then I can show you the pretty Mandelbrot set. Now I mentioned that we're going to have to get some code installed. Just a little quick poll, how many of you are on Windows? How many on Mac? How many Linux? Okay, right. And how many don't have access to the internet? Okay, tricky. All right, so this is the Mandelbrot set. Out of all of the solutions that I'm going to quickly run through now, and I'll just show you the specific timings. We're going to preserve exactly the output, so we've got a validation number which counts up all the pixels inside that display. So we know we're always getting the same result coming out. If I just show the same thing in Python, zips fast, way quicker, and that's around 10 seconds or so on this machine. which is a fairly slow machine. It's a 4-year-old MacBook. There we go, 8 seconds on that solution. Going to Cython, compiling the pure Python, and then adding a lot of type annotations, giving a lot of hints, we get down to 0.6 seconds, and we'll have that done within the first hour tomorrow. That's a really nice result. And Shedskin as well, taking the original Python version, 0.4 seconds. So we'll have that done about 8 minutes after the Cython version tomorrow. The hiccup being that Shedskin won't work with NumPy codes. If you want to use any of the higher level functions in the numeric Python library, you can't use Shedskin or not in an efficient way. But the author assures me as of 2 weeks ago that he's working on that problem now. NumPy vector, I'll run that, that's going to take an absolute age. This takes the same 50 seconds. So it's kind of interesting looking at how many of you have experience with the numeric Python library NumPy? A couple of you, okay. And how many of you know it, never looked at it? A couple of you again, okay. So normally with NumPy, we use NumPy because we have very large arrays and we want to perform the same calculation on every item in the array. Super efficient for that. Turns out that the Vanderbilt set, most of the time you want to drop out before you've done all of the iterations you can possibly do. So NumPy is sitting there calculating all the iterations for all of the items. So it's doing way more work than any of the other solutions, which is a bad thing. But I'm going to use that as an example. It's one where you have to think about what is the right solution for the problem that we're solving. And also it's a really friendly introduction to vectorized calculations in NumPy. It's 3 lines we have to deal with. So 54 seconds. But if we take the numeric expression version that I mentioned, where you just take a couple of words and wrap them around your original expression, and ends up using both, of course, the CPU meter at the top here, all of a sudden it tops out very nicely. And so even though we're using just relatively straightforward Python code, now we're very efficiently using the CPU. The NumExpr library is compiling, it's reordering all the expression, compiling down as best it can in the background. And we go from 54 seconds down to 19. I'll teach you that in 2 minutes. Cython NumPy looping, so it takes no time at all. So this is another way of using NumPy, going away from the vectorized form and switching to the same looping that we did for the first example we first looked at, the 54 seconds, with Python doing big for loops, but giving lots of annotations, and then with Cython it comes down and it takes 1.5 seconds. Really, really nice, quick solution. And then the multi-processing one. Interesting thing here, we've got this calculations running on 2 cores asynchronously. And so you see the result that's scrolling up. No longer is it always ordered, but it's not in perfect sequence. That's because 2 cores are running on half of the problem each and reporting their results back as they go. So we've got 40%, 80%, 90%, 100%. And then these 2 will come back. And so this takes as long as the Python version of 1 core divided by 2, because I've got 2 cores here. And then I won't show these last 2 because they're going to look the same on this machine until we look at the code tomorrow. Here I've got a parallel Python implementation, so it can work on multi-core and multi-machine multi-core, which I want to have running in a little cluster of us tomorrow. And in this version, it's using a Cython binary compiled module, which is the result of about 2 hours before the tutorial. The one thing I haven't figured out how to do yet, and the community behind Parallel Python, no one seems to want to give an answer either, so I'm going to try and figure it out tonight for you, is how to take a binary compiled static module that's come out of Cython and automatically distribute it using the module mechanism across all of the machines in the network. And as long as we're in the right environment, so other Macs in the room, then the Cython compiled environment will be distributed. It'll run locally and then clean itself up afterwards, such that we can rapidly prototype on 1 machine and deploy to 10 machines just quickly. That'll be a nice result. I'm not sure if I'm going to get that done by tomorrow. If not, the write-up that comes a couple of weeks later will have that in there. And in the final version, this one's going to run on the graphics card. So this one, on this graphic card, it's an old machine, single precision only. The eagle-eyed amongst you will notice that the validation number that comes out is different. That's because we're using single floating point precision rather than double. This is still running. There's no with the CPU graph, which rather than CPU usage, that's only data transfer. So that's the slow version. And then if we go with a little bit of C code, 2 lines of C code wrapped up in Python, then the same thing comes back far faster. And this 1 second result here is the same as 0.07 second result that I showed earlier. So, 2 lines of slightly replicas. Now, the other thing we're going to do, I'll just flip through this bit. We're going to look at the profiling that I mentioned and look at Run Snake Run, which is a nice visualization tool, which will help us to guide the optimization. It won't actually help us guide it very much in this case, but it's very useful when you've got more than one function that's slow, which will be the normal case. But we'll quickly move on to the line profiling module, which gives us, if you're going to use rational rows, say, in a C development environment, then you get line-by-line timing, and that's incredibly useful. And then we're going to go through all the ways that we work from the simplest version of the problem to the more complicated versions, changing the code all along the way. And you don't want to see that yet, because you want to come along tomorrow. Oh, and yeah, a couple of little bits. We'll look at some graphs for what happens if I vary the cache strategy. There's a couple of little results there which are interesting. And then we'll end up with some questions for you. Okay, well, that's the size of the tutorial that you're going to get tomorrow. So we can call this off here unless there are any obvious questions right now. For anyone who would like to take part tomorrow, it'll be really useful if you just come to the front and I've got 4 USB keys, take a copy of the directory and get as much installed now as possible. Or, said earlier, as long as you're on the access point at the top, then my machine is serving this directory, and you can just grab, I'll show you what it looks like. It looks like this. So there's a Linux.zip, a Mac.zip, and a Windows.zip, and all the individual components of it. I've tried to segment it. I think I've got everything in there. I've probably missed some bits. Hopefully, if we've got most of it installed on most of the machines, we can fill in the gaps tomorrow early. So either go to that access point. You haven't got to be authenticated, just on the access point, and then go to this IP address of 38,000 and grab those files, or come to the front and borrow the USB keys. And then we'll get set up. Any questions? Questions? Cool. Okay, well, thank you for your attention.